Hello, my name is Austin Garcia, and this is my video presentation about classification on bank churn data. We were given an Excel file that contained data from a bank, geography, the customer ID, their surname, their estimated salary, account balance, tenure, and so forth. And we're supposed to use these variables to create models that would predict the exited column. So if the customer exited the bank or if the customer stayed with the bank. So that's what we were trying to predict. So we have, starting with part 1 here, the EDA, open the file obviously. We have some information about it. Checked for duplicates. There weren't any. Next, I ran a couple means just to kind of get a feel for it. I wanted to see, so the mean salary of exited and mean salary of stayed, mean credit score of exited, mean credit score of stayed, mean balance of exited, mean balance of stayed. I did this just to see, if maybe the people with higher salaries stayed or left, and what the credit scores would look like for the people that stayed and the people that exited, and then what the account balance of was the people that stayed and the people that left. And some interesting findings. The credit score was pretty much the same. I mean, there's a little bit smaller for exited, and then for the mean salary here, looks like the exited is just a little bit higher, but for account balance, so the amount of money that they would have had in their balance when they left, the people that left actually have a higher overall balance than the people that stayed on average. The next one I wanted to do was basically calculate the average tenure of people that exited, the people that left, and it's pretty similar at about 5. Next, I made a histogram here of the distribution of ages. I just kind of wanted to get a look and feel for, what the age range was. And it's mostly people within their 30s being the bulk. And then here we have just a tiny little bit of people after the age of 70 and above, just a little tiny bit. And then we have a heat map here, basically with the correlation to the exited variable. And beforehand, I went ahead and dropped basically these. You can't really, and we're non-numerical. So with the 10-year, looks like they have a very weak correlation. Balance has a weak positive correlation. Number of products has a moderate negative correlation. No real relation between has credit card and exited. Is active member has moderate negative correlation. And yeah, these were the two graphs that I made for EDA. And then moving on here to pre-processing, we have the data cleansing part. So dropping useless features. I went ahead and dropped, I just kind of want to take a look at geography here. So we have France, Spain, Germany. Those are the only 3 countries, that were available. And obviously France is pretty higher compared to Spain and Germany. And I kind of, explained a little bit more in depth why I wanted to drop it here. But basically, I didn't think that was just very useful. And France was so much higher than the other ones. I just didn't think it would be that. I feel like it would have just been noise when building the models. And it's only 3 countries, so I just thought that wasn't really going to be super useful, so I did drop that one. And I also dropped here customer ID and surname because I just didn't think those, customer ID, I just don't think either of those would be useful, at all. Next, we get into the filling nans appropriately. I just checked for nulls, and there wasn't any for any of the ones I have here. So then I went on to the outliers, just kind of getting a feel for the mean, the standard deviation of each of these. If the standard deviation is significantly different from the mean. And then for here I made some box plots to look at some outliers, and there's not really anything crazy here for estimated salary or for balance. And then you have the credit score and age. There does seem to be, I don't really, kind of seems to go all over the place, but this makes sense given the data set. I mean, credit score and age is going to be unique compared, it's going to, it's an individual basis. Those are going to be unique to each individual. So even though, there's, clearly a couple outliers here, I didn't think these needed to be filtered because I felt like that would actually kind of limit the model, because you wouldn't be capturing, people with really high credit scores, if that could be a factor. That could be a factor. Or, what about age? Like, what about people that are older? Do they tend to leave at a little bit of a higher rate? So I didn't want to filter these because I thought they were so unique compared to. I thought every individual is going to have a different age and credit score, so I thought these would still be useful. Tenure, no real extreme values there. And then for number of products, there was one extreme value right here. Someone has 4 products. Everyone else only has 2. So I did filter this one out because this guy, he just had 4 products. So I just, I didn't think that would be very necessary. So I just filtered that out and kept it, anything greater than 2 was filtered out of the data set. So here's me filtering out the outliers. So next I checked the distribution of the binary variables, have credit card and is active member. And it looks like for is active member, pretty even split. And obviously there's going to be a little bit of majority for, credit card because most people have a credit card. I would definitely be in this one because I don't have one. So then we get here to the feature engineering. Categorical and binary features, label, ordinal, encoding, or dummies. So I had to make dummies for, obviously, these two. The binary ones has credit card and gender. So I made the dummies here for the encoding section. And then here we go for the scaling and transformation. So if you kind of go up here to this section, and I talk about this in the markdowns, you can see just how out of scale everything is. So like 0 to 10, 1.0 to 4.0, 20 to 90, 400 to 800, and then you get some really crazy ones, 0 to 250,000, 0 to 200,000. So these are definitely out of scale completely. So for this step, I used 2 different scaling methods, the standardize and min-max. Didn't really end up mattering in the end, but I'm not going to spoil what's up ahead. So I made 2 different scales just to try and see if there'd be any differences. The standardized scale, then here is the normalized data frame. And then here's just to check, the distribution for transformation. There was nothing. I thought it was pretty evenly distributed, so I didn't actually bother with the transformation. So here we get to part 3, the modeling section. So the first model I built was the KNN model, and the first time I ran it, I actually ran it on base data frame, which is basically just my data frame prior to scaling. And the reason I did that was because I wanted to make sure that my scale data frames were performing better than the base data frame, because obviously if base was performing better than scaling, then I did my scales wrong. So, and then I'd have to go back and change that. So I ran it, I ran the base data frame without any scaling using KNN, and I got a 79% accuracy. And the base still has the filtered outliers, the dropped columns. The only difference is that it just doesn't have the scaling. It's not the min-max or standardized scaling. There's no scaling a 79% overall accuracy. So then here is the KNN model for standardized. And like I said, I just wanted to do base data frame just to make sure that standardized and min-max were performing better than it, so that if it wasn't, if there was some kind of, scaling, the scaling wrong, I could go back and change that. So here for the standardized, we actually have an 84% accuracy, which is about 5% better than base data frame. And then for min-max, it's also 84%. So it was about the same for both. And then so for my next model, I used light GBM. I didn't bother doing the base data frame since the scaled ones did better. So I didn't use the base data frame for any more models. So for light GBN model, actually for both of the standardized and min-max, we got 86%. This is actually the highest overall accuracy that I got, was 86% using light GBM. And then here's the light GBM for min-max, which is also, gotta scroll up ahead, which is also 86%. And so the next model I built was the decision tree, and decision tree actually performed worse than the other two at 79%, which the base data frame on KNN did 79%. And so this is the scaled data frames, and both of them got a score of 79% on decision tree. So of the three models built, the decision tree is definitely the worst performing one overall compared to the other three. And that was sort of my conclusion, was that the overall best one was light GBM, and KNN performed second best, and then the decision tree performed worse. I know I'm kind of going over here, so I'm going to make it quick. I would say the most difficult part about this was actually getting the models to run on my computer. I had a lot of trouble getting some of these to run. Actually, on some of them, I had to pick a lesser one, like for light GBM. I picked light GBM because that was less taxing on my hardware. So yeah, my laptop's a little bit older, and so that would be the big issue. It would take like 5 minutes for it to run. Thanks for watching, and have a good night.